In this video, we're going to go over the different sets of real numbers and properties of real numbers. We begin with the idea of the real numbers are all the numbers that we are used to working with that are what we would call not complex numbers. For instance, we would have numbers like fractions, 3/4, 1, -1, 10,000, -10,000. But the real numbers can be split into two smaller categories: the rational numbers and the irrational numbers. Now, rational numbers are any number that can be expressed as a fraction of integers. So, for instance, 1/2, fraction of integers. You could even have 2/1, -10/5, 1,000/37, any fraction of integers. Irrational numbers are most easily stated as just any number that is not a fraction of integers. In this example, we might think of the square root of 2, the square root of 3, but would be a not example of this is the square root of 4, because the square root of 4 is actually the number 2, which could be expressed as a fraction of integers. So we would want something that's what we might call an irreducible square root. So this is the quality of all the irrational numbers. Next, we're going to look at the rational numbers. Within these rational numbers, as y'all can see here, I've already expressed some that actually could be more carefully considered to be integers. 2/1 is the same as the fraction 2. Okay. -10/5, while it is a rational number, more specifically it's an integer because -10/5 equals -2. Integers are kind of like -5, -7, -10,000, 0, all the way up what we might think of as nice whole numbers, though we do want to distinguish that because there's actually a name for whole numbers that means something other than the fact that it's just an integer. Whole numbers are the integers that start at 0 and then go on to positive infinity, so 0, 1, 2, 3, and so forth. Natural numbers are just the numbers starting at 1 and increasing through the positive integers, 1, 2, 3. And these are different classifications of real numbers. The smallest category is the natural numbers, and then the whole number actually just adds one additional element, 0, to the natural numbers. Then we have integers, and the way integers expand this is they now consider negative integers. Specifically, that expands past the whole numbers, -3, -2, -1, 0, 1, 2, 3, and continuing. And then we've got rational numbers that includes fraction of integers. That's all of this category of real numbers. And then we've got the irrational numbers. So based on this discussion of these different categories, we might want to answer the question, is it possible to have something that is considered a natural number, which we know is the positive integers, 1, 2, 3, continuing on? This ... means the pattern continues forever based on the pattern that was already set. So the next entry would be 4, 5, and so on. That is also a whole number. Okay. Whole numbers we know start at 0 and increase by 1 forever and ever. So 0 plus the positive integers. In this case, we would say, yes, this is possible. And we have actually infinitely many correct examples. 1 is a natural number that is also a whole number. So is 2, so is 3, on and on and on. We might ask ourselves, could we have a whole number, separate question, that is not a natural number? So something that belongs to this category, but not this category. Looking at that, we would see 0 is the only one that fits this. Yes, the only option is 0. Next, we'll think about our next question. Is it possible to have an integer that is not a natural number? Let me turn back to our screen before. So we are in the category of integer. So we want to know, is there an integer that is not a natural number? And the natural numbers are only 1, 2, 3, and on. So any number that is 0 or negative would definitely fit the category of integer but not a natural number. And any of these would be what we might call an example of that, something that's an integer but not a natural number. Next, we're asked, is it possible to be a rational number that at the same time is also an irrational number. Let's look back at our diagram. So we were asked, could we be a rational number, any of the things in this group, and at the same time be an irrational number? Now looking at these, we could consider these to be Venn diagrams, and do we see that the rational numbers and the irrational numbers are completely separate? That means they have no overlap, and that makes sense because remember, irrational is just defined to be not rational. So our question that we were asked here, so in conclusion, it is not possible to be both rational and irrational because by definition, irrational numbers are not rational numbers. In this next example, we've been given just a different sampling of numbers and we want to fit them into all possible categories that they would apply. We know that the largest category is the real numbers, so we might start here and then move upwards. So real numbers, none of these are what we would call complex numbers of the form a plus bi. We're not going to see that in this class, so all of these would be considered real numbers. Let's write those down. The next category that we might think of is we know real numbers are split in between two categories, rational and irrational numbers. Irrational numbers are numbers that can't be expressed as a fraction of integers, and specifically for our class, we're going to look at what we might call irreducible square roots. Specifically, the square root of 2 cannot be reduced any further, so it could not be rewritten as a rational number. That's going to be our irrational. But all these others could be written as a fraction of integers. For instance, any integer, -5, can be written as a fraction by simply just dividing it by 1. -5 over 1 is -5. -1/3 already looks like a fraction. We could deal with 0 in a similar way. 11/4 is already a fraction of integers. 4 we could think of as 4 over 1. And now specifically, we're going to turn our attention to this number. Can this decimal place be expressed as a fraction of integers? See that we've got 3 decimal places here, and think of every decimal place. The way you would translate this into a fraction is if you move the decimal place over once, that's multiplying by 10, over twice, multiplying by 100, 10 times 10, over again, that's multiplying by 1,000, 10 times 10 times 10. So the decimal 5.422 could be expressed as the fraction 5,422, all divided by 1,000. And the reason we knew to divide by 1,000 is we divided by, since we had to move the decimal place over 3 times to express this as an integer, we would have to divide it by 10 to the third, or 1,000. We've split up our real numbers then into the rational and irrational. We know that within the rational numbers there are more subcategories. So we've already made this division. Now we need to consider we are in the rational numbers. How can we corral these into more subcategories? So we would next look into what would be considered just integers, then whole numbers, then natural numbers. Very quickly we see that -5 would be considered an integer, as would 0, as would 4. What would be considered a whole numbers is all the non-negative integers, so 0 and 4. And finally, the natural numbers would just be 4 because 0 is not considered to be a natural number. So we've rewritten all the different values and we've labeled them to each of their relevant categories. Notice that there are some entries in multiple categories, and that's the idea of that embedded diagram. Everything that's a natural number is a whole number. But the reverse is not true, as we saw in our previous example. Not every whole number is a natural number. So think about how that inclusion spreads outwards. With any kind of number system, we're going to want to compare values to say this value is larger than the other, smaller, greater than or equal to, and to do so we're going to use inequalities. We've got 4 different inequalities that we want to define so that we have them for future notice. I'd like to draw our minds to a key distinction between them. Notice in our first 2 statements, it's just this diagram here, whereas in the second 2 it looks almost like a copy, except for that we've got an additional line underneath each of the symbols. This additional line means an or equal to. So these would be what we would call strict inequalities. It's strictly greater or strictly less than, and these next 2 would be considered less than or equal to. Let's write out how we could translate these statements in words. Our first statement should translate x is less than y. X is greater than y would be the second statement. And an easy way to remember how this works is you can think of it, there's a few ways. One of them is that the point of the angle points to the smaller number. So in this case, since the point was pointing towards x, we know x is smaller than y. That's where we get the translation x is less than y. Whereas in this case, the point was pointing towards y, so y is the smaller number. So you could either say y is less than x, or the equivalent statement of that is that x is greater than y. And then it would be a very similar idea, except with this additional line here, we would now say x is less than or equal to y. And similarly, our last statement would be x is greater than or equal to y. Equivalently stated, y is less than or equal to x. So with this notation, let's translate this verbal statement, 5 is less than 8, into this mathematical notation. So 5 is the smaller number, so we know the point should be facing the 5. So 5 is less than 8. That is a true statement. Think about how we might state this next one. X is greater than or equal to -5. So in this case, since x is greater than, the point should be facing away from it. And then the or equal to statement includes the line underneath to show that equality is allowed as well. X is greater than or equal to -5. Alternately stated, -5 is less than or equal to x. With this example, we're going to introduce just two more notations that we might have seen before or not. This is just the equal to symbol, whereas this next one, the equal to symbol with a line through it, means not equal. So this is saying 6 is not equal to 6. Okay, that of course is a false statement. 6 is equal to 6. 3 is equal to 9 is false as well. That's not true. Now here we don't need to just say, are these visually equivalent? We want to say, are they numerically equivalent? So 3 is not visually equivalent to the symbol square root of 9, but numerically it is equivalent because we know the square root of 9 is actually the value 3. So this is a true statement. 3 is equal to the square root of 9 because the square root of 9 is 3. So this would be true. Now we're not just talking about equality, we're wanting to compare the value and the size of the number. So square root of 100, is that less than 20? It would help us if we could simplify what the square root of 100 is. Now if we know off the top of our head 10 squared is 100, then we know the square root of 100 is 10. But also in any simple calculator that you have that does more than just addition, multiplication, subtraction, and division, you should have a square root button. So for more complicated square roots, you could always type the square root of that number. It would get the decimal form, and then you can actually compare the values. So with these, it's helpful to simplify the expression first before you verify whether the statement is true or not. So I could rewrite this as correctly 10. Is that less than 20? Definitely 10 is less than 20, so this is a true statement. Remember, the point points to the smaller number. So this is saying 20 is smaller than 35. Equivalently, 35 is greater than 20. We have to think, is that true? Yes, it is. And if you're ever curious, you could also draw a number line. 20, 35, definitely 20 is less than it. So that is a true statement. This next one, is 12 less than or equal to 12? Take a moment to consider it, and also consider the similar but different statement, 12 is greater than 12. Our first statement here, 12 is greater than 12, is actually false, because a number is not bigger than itself. It is exactly equal to itself. But our next statement, since it includes the or equal to line, leaves open the possibility that the two numbers could be equal. It doesn't have to be strictly greater. So this statement would be considered true. Here we might want to look at our number line first, especially when we're dealing with negatives. If I was just drawing a quick number line, the negative number does come before the positive number. So now let's rephrase this. We know -3 is less than 5. Let's see if this is what the inequality says. The point is pointing to the smaller number, so it is saying 5 is smaller than -3. We know this is not true because larger numbers lie to the right of the number line. So this would be a false statement. Let's make a number line for our next one, -2, and then 0, and then positive numbers. Is -2 smaller than 0? Definitely it is, because it's to the left of 0. That's true. Is 0 less than 5? Also true. And here's an idea that why don't you take a moment to create an inequality that is true as well. And if you like, feel free to send me a picture of your work via Canvas. This would not be for a grade, but it would just be to, that way I can check what you wrote down to make sure it's accurate. So write it there and send me a picture through Canvas message if you like. Our next topic in discussing real numbers is the idea of additive inverses. All an additive inverse is a number that you would add to another number in order for the overall sum to be equal to 0. We know that in this case, whenever we're adding, if we think of this in terms of a number line, you would want to find something that is equal distance away from 0, but in the quote-unquote opposite direction. So if we start at 4, we see we are a distance 4 away from 0. And if we want to find something that we could add to this 4 to get to 0, we need to cover the same distance, but in the opposite direction. This would bring us to the idea of -4, which is still a distance 4 away from 0, but in the opposite direction. And definitely, just from our addition facts that we learned as a child, -4 plus 4 equals 0. This is the definition of additive inverse, and it goes in both directions. 4 is the additive inverse of -4, and -4 is the additive inverse of +4. So our definition in general is if we start with some number b, then the additive inverse is just going to be the same distance away from 0, but in the opposite direction. We indicate opposite direction by a negative symbol. B plus -b, we know that would equal 0. So -b is the additive inverse of b, b is the additive inverse of -b. Now we need to ask ourselves, what's the additive inverse of 0? In terms of our idea of equal and opposite distance away from 0, or equal but opposite distance away from 0 direction, 0 is already at 0. So we don't have to move any distance to stay at 0. The idea is if you add 0 to itself, you still get back 0, which makes 0 the unique real number that is its own additive inverse. So in this example, we're going to ask to label 0, 1, 5, and then 9, and then also label their additive inverses. Let's first place these on the number line. Remember, with the number line, smaller numbers go to the left of the number line, larger numbers go to the right. So we might first place 0 here first. So 0, 1, try to pay some attention to scale, 5, and then 9. And then let's one by one find their additive inverse. We know 9 is 9 units away from 0, so its additive inverse would be 9 units away from 0 in the opposite direction, which would be -9. Similarly, the additive inverse of 5 would be -5, additive inverse of 1, -1, and then the additive inverse of 0 is just itself 0. Now, whenever we start working through different operations on real numbers, we're going to want to be aware of the fact that if you have a negative of a number that's already negative, that actually turns the number to be positive. It's like the idea of subtracting a negative number means you're actually going in the positive direction, that amount. So we have the rule that negative parentheses -x, when we distribute the negative throughout, will just give us the positive value of just x. And this you might think of the double negative rule. So an example of this is -3 is actually the positive value, +3. And what we just talked about here is kind of the idea of the absolute value. Absolute value doesn't care which direction you are away from 0, whether you're at -7 or +7. All that it's trying to determine is what is the distance away from 0. So the absolute value of -7 is just 7 because we think about distance as a positive quantity. It's saying that -7 is 7 units away from 0. So the absolute value of a real number is the undirected distance between 0 and the number on a number line. The symbol for absolute value are these straight vertical lines. So the absolute value of +7, 7 is 7 undirected units away from 0, so that's just 7, which is equal to the absolute value of -7, also 7 units away from 0. What we'd want to be cautious about, though, is whenever we layer rules within absolute value. So if we were looking at a new example which had negative the absolute value of -5, we would not want to apply the same double negative rule here because of the distinct difference in the operation. These parentheses just mean that we're distributing through the term, whereas these vertical bars actually represent the idea of absolute value. They mean you have to first find the absolute value of -5. So we'd have to think first, what is the absolute value of -5? That is 5. That's the undirected distance away from 0. Once we've found that, then you apply the negative. So notice I've changed my notation from absolute value. Once I found it, I'm using the parentheses here. And then we distribute the negative, and we would end up with -5. So when it's just absolute value by itself, it always turns the number positive, but if there's other operations layered along with it, you need to find the absolute value first, and then distribute through the other terms. Okay, we went through this example, but the absolute value of -7 would be written as the absolute value bars, -7, 7 units away from 0, as is the absolute value of just +7, also 7 units away from 0. So let's look at some order of operations first. We know the absolute value of 4. 4 is 4 units away from 0. Absolute value of -4. -4 is also 4 units away from 0, just in the opposite direction. This is where we need to be cautious because these are different operations. This is the absolute value of -4, whereas this is the -1 times the absolute value of 4. We would first consider that the absolute value of 4 is just +4. Then we apply the negative. -1 times 4 is -4. And the reason I'm saying -1 times 4 is when you just see a negative symbol, it's implied multiplication by -1. We just don't write it because it's just a little bit more efficient to just write the negative symbol, but that's what's implied to be occurring. I'll give everybody about 15 seconds to think about what your answers would be for here, and if you need to, definitely pause right now, answer these, and then when you've finished working on it, unpause, and then you can see if we got the same answers. Now, as a check to your work, we know that the absolute value of -12, we would consider that first. That simplifies to just 12. And then we still have the -1 lingering in front, which we know is an implied multiplication by -1. Definitely -1 times +12 is -12. In this example, we first need to consider what is 8 minus 3. We've got to simplify that first, and then we take the absolute value. 8 minus 3 is +5. So then we had the absolute value of 5 is where this would simplify. Absolute value of 5, just 5. Similarly, in our next example, we need to consider what is the 9 minus 4 first, because we need to know the simplified term before we can take the absolute value. 9 minus 4 is 5. So I'm looking at negative the absolute value of 5. I know the absolute value of 5 is just 5, so notice the difference in notation implies a very difference in expression. We now have the numerical answer 5 there, times -1, which is -5. In this next example, we're going to look at some applications of real numbers in terms of change representing growth or decrease. So whenever change is representing growth, the value of the change is positive, and whenever change is representing a decrease, the value of change is negative. So we have that the Consumer Price Index measures the average change in price of goods and services purchased by urban consumers in the United States. The below table shows the percentage of change in the CPI for selected categories of goods and services from 2009 to 2010, and then from 2010 to 2011. Use the table to answer your questions. Why don't you pause the video now and just examine this table, read through our 2 questions, and then unpause when you're ready to hear the discussion about them. Now, as we're reading through, we're going to key into phrases like increase and decrease, because that will indicate the sign, whether the change is positive or negative. Which category, in which set of years, so 2009, 2010, 2010, 2011, represents the greatest percentage decrease. And from this careful reading, we know that just because we're looking at decrease, the change should be negative. So we're only going to concern ourselves with the negative values of change in the table above. Let's look and identify those. So every entry in this table represents change. I've identified the only negative values of change, And if we're looking for greatest decrease, we would want that percentage of change to be a negative number that is farther negative than the other. So further to the left, that means farther away from 0. Looking at these, we would see that negative 4.5 is the furthest negative number away from 0 if you imagine the number line. So that means we had the greatest percentage decrease in the category of appliances during the years 2009 to 2010. We can record our answer here. Our next question asks us, which category in which years represents the least change? Now notice in this example, they don't say the least increase or the least decrease, they just say least change, which means we are just looking for the number of change that is closest to 0, regardless whether it's positive or negative. So we are going to be looking at numbers that lie very close to 0 on the number line. Looking at our options above, I'm going to circle some of the numbers that are closest to 0, and then we can figure out which would be the least among those. Definitely negative 0.4 seems very close to 0, just going down the list in order. Negative 0.1 is kind of close, 1.3 is kind of close, and all the others are farther away from 0 if we imagine a number line. So between these, thinking about these represents the least change, that's which is the closest to 0, and I think that would definitely be the negative 0.04, which is from housing in 2009-2010 is how we would read this table. So we'll record that. So that's it for this lecture. Be sure to check out our class's Canvas page for the relevant homework for this section and any quizzes and follow-up information, and we'll see you in the next video. Thank you.